here in this lecture, actually, we are discussing the cavity lifetime, T sub c, which is the time taken for the intensity of light introduced into the cavity to decay to 1 over E of its value. And you can see we have two mirrors here, and the distance between these two mirrors is L. And you can see at T equal to 0, energy density rho of nu, traveling backwards and forwards between the mirrors. Absorption and leakage occurs. Energy density rho of T can be given by this equation here. And we can derive the relation d rho by rho is the fractional loss of energy in the time dt, defining dt transit time of light between mirrors where all equal to mirror separation, as we said. And we can go by this derivation, by this to find out. It means that we have to invert the population such that n2 larger than n1 by 8 pi squared nu t sub 2 t over cubed c t sub 2 1. As well, here we must define the threshold power and find the meaning of the threshold power and calculate how much power needed in the system to achieve the threshold condition for oscillation. Need at least n2 minus n1 excitation amount of energy, which is equal n2 minus n1 multiply h nu. All these have to be achieved in a time which is less than t sub 2, 1 spontaneous lifetime for the atoms, and the minimum power required, rho minimum, equal to n2 minus n1 multiply h nu over t sub 2 1. And if we go by the revision here, we can find the power required proportional to 1 over cubed lambda. It's more difficult to produce UV and X-ray laser than an IR laser, and we can reach the min. Also, the very important things here in our lecture, the spectral line width, and we have two types, the natural line width of the laser, which is called also Lorentzian line profile or homogeneous broadening. This is one of the types, and we say this is Lorentzian because it's actually have the Lorentzian shape, as it's clear in this here. And the relation represent the Lorentzian profile as delta nu 1 over 2 pi tau I. And also we have the second type, which is the Doppler line width, also called homogeneous broadening. And this is actually one of the major contribution to the spectral line width in gases at low pressure is the Doppler width, which is due to the thermal motion of absorption of emitting. In this here, we can see the observer looking towards emitting, and it's very important. And the shape of the in this lecture, you can find the by derive the equation here, you can reach to the final equation for the Doppler line width.